Section 9.1 Introducing Engine Terminology. In Chapter 8, we considered vapor power cycles. Water was used as a working fluid to carry out the thermodynamic cycles. Now we are going to study gas power systems. As the name implies, a gas is used as a working fluid, and air is the common working fluid in the gas power systems. Gas power cycles are reciprocating engines and rotating gas turbine engines. Reciprocating engines can be classified as spark ignition engines and compression ignition engines. Spark ignition engine is a very common type of internal combustion engine. The combustion is initiated by a spark plug. Compression ignition is also called diesel engines. The combustion of the air-fuel mixture is initiated as a result of high pressure and high temperature of the mixture. Let's take a look at the piston cylinder assembly. It has an intake valve and exhaust valve for air and fuel. TOD, or top dead center, is the position of the piston when it forms the smallest volume in the cylinder. BDC, or bottom dead center, is the position when it forms the largest volume in the cylinder. The diameter of the piston is called the bore. Stroke is the distance between TDC and BDC. The minimum volume formed in the cylinder when the piston is at TDC is called the clearance volume. The volume displayed by the piston as it moves between TDC and BDC is called the displacement volume. The compression ratio, R, is defined as the volume at BDC divided by the volume at TDC. So it is the ratio of maximum to minimum volumes. Or it can be expressed as the sum of clearance volume and displacement volume divided by clearance volume. So the compression ratio is greater than 1. Most internal combustion engines are 4-stroke engines. The piston makes 4 strokes in a cycle. The 4 strokes are intake, compression, power, and exhaust strokes. First, intake stroke. The intake valve is open. The piston moves from TDC to BDC. For spark ignition engines, air-fuel mixture enters the piston cylinder device. For compression ignition engines, only air enters the device. Compression stroke. The intake valve is closed and the piston compresses the mixture, moving to the TDC. Power stroke. The piston is at TDC and the air-fuel mixture is ignited by a spark. For compression ignition engines, this is when the fuel is injected and the combustion takes place. The piston returns to the BDC. Exhaust stroke. The exhaust valve is open. The combustion products are exhausted. Another term we often use in the internal combustion engine is the mean effective pressure. The mean effective pressure is defined as the net work for one cycle divided by displacement volume. The net work can be expressed as W net MEP times displacement volume. On a PV diagram, pressure volume diagram, consider the network produced by a piston cylinder system. The enclosed area represents the network. And this is TDC, the minimum volumes. This is BDC, maximum volume. Now imagine another piston cylinder which produces the same amount of network. It has the same BDC and TDC. So the displacement volume is the same. Now a constant pressure is acted on the piston for the entire cycle, and it would produce the same amount of network. So this area by another piston is same as this area. So the enclosed area for both cases are the same, and the constant pressure is referred as mean effective pressure. The higher mean effective pressure means the greater network. It is useful to compare the performance of reciprocating engines of the same size. The MEP value tells us how well an engine uses the displacement volume to produce work. The actual gas power cycles are complex. The working fluid is not just air. It is a mixture of air and fuel. The physical and chemical properties of the mixture change during the thermodynamic cycle, and the initial and the final stage of the working fluid in the actual cycles are not the same, as fresh air is introduced each cycle. But we simplify the analysis of internal combustion engines using the following air standard assumptions. First, the working fluid is assumed to be air, and it is considered to be an ideal gas. No chemical reaction takes place in the system. It has a fixed mass in the system, and the system is considered as a closed system. Second, the combustion process is replaced by a simple heat transfer process or heat addition process from an external source. Third, there are no exhaust and intake processes. The exhaust process is replaced by a simple heat transfer process or heat rejection process. Fourth, all processes are internally reversible. Lastly, the specific heat of air is assumed constant, and the value is evaluated at ambient temperature value, 77 degrees Fahrenheit or 25 degrees Celsius. This assumption is called cold air standard analysis.